What I'm going to present is just maybe a little bit different angle on the way we solve system of linear equations. In particular, we will look into that from the sort of from the rigorous point of view, how we can solve it how we can come up with the algorithm which will solve everything. The main purpose of this, of course, not because we want to solve everything, just because we want to have like a broader picture of what's happening with the system of linear equations. Because when you have a broader scope or broader picture, you probably see far beyond just this elementary task of solving of system of linear equations. So I will start with how we normally look in general on a system of linear equations. It's quite a long writing. So when you try to analyze a system of linear equations from the general perspective, you have to first give a general look of a system of linear equations. And generally, system of linear equations is something like this. You have we will look into system which have many equations and many unknowns, and this many, I said this word many 2 times. Now I will make an index. I will use an index to represent this many. So the first equation in my system, it may look like this. That would be left-hand side. A with double indices, they represent the coefficients. X with single index, they represent the unknowns. And so my many unknowns now becomes n unknowns. This is the right-hand side of my first equation. Second equation may look like this. You see my first index in my A numbers. It represents the index of the equation, whereas the second index in my A numbers, it represents the index which corresponds to the unknown. So that will be the second equation in general. You will have many like this. I will give you the look of the last one. You see, I use the letter M for Mary, which represents the number of equations. That's the index for another. Many, I said before. So we have many equations, many unknowns. And that's how generally a system of linear equations looks. You're not going to write this very often, but once you probably have to look into that. You can put the bracket here, just to combine them together. Here's my system of linear equations. In general, we can say that my coefficients, they in general complex numbers. So m and n are integers. Coefficients, both left-hand side and the right-hand side, they are complex numbers. In general, they may be complex numbers, even though probably you won't see many systems which actually have complex numbers in them. In principle, the methods even the methods you have right now, they in principle will work for the systems with complex numbers, even though the computationally it will be a little bit harder to perform those methods. Unknowns also in general will be some within the complex number scope. Yeah, so when you write something like this, normally you have to specify, because you see, rather than saying A11 is a complex number, A12 is a complex number, A1n is a complex number, A21 is a complex, I rather saying all of this, I just said it in one short sentence like this, by using these J and K letters. When you do this sort of writing, when you do this sort of abbreviations, you have to specify what's J and what's K, and that's my specification. J is any index between 1 and n, 1 and m, sorry, and K is any index between 1 and n. Now, the method which is like the fundamental method, the general method of solving of system of linear equations is called the Gaussian elimination method. I will show you this method on the next slide. The objective of that method, the method itself, you should understand this. The value of the method actually not in the fact that you can solve any system. It is a value of that method, but it's not the main value of that method. The main value of that method, it gives you completely different look into the system of linear equations, and that actually make it easier to look beyond the system of linear equations. Unfortunately, probably I can't carry all of the importance of that method right now. Trust me, you will appreciate that at later stages of your mathematical development. But the objective of that method, on the practical side, the objectives of that method is to convert any system to what is called the triangular system of linear equations. And the triangular system, it is in formal term. The proper term will be what is called the reduced form of the system of linear equations. I will define this proper term later, but triangle is like a It's a geometrical term which describes the shape very closely. It's a system, and I'll give you the example of that system. It's a system which has the structure like this. It's a system of three equations in three unknowns. This is a kind of system which I call right now informally triangular one. The advantages of having such a system is that we can easily solve that system. Right? It's a cube. It's an immediate computation, immediate solution, or immediate steps which will give you the solution to this system. So the objective of this general method, of Gaussian elimination method, is to convert any system like this to the system of this type. It says here that this is a system which is taken from the page 3. Because if you have a system like this, you can solve it straight away. And actually, the method of solving it has a name. It's a good name to remember. It's called back substitution. So if you have a system in this form, you can easily back substitute. And this is just the abbreviation to say you can easily solve for every unknown, because the last one, if you solve it, the last equation, you will have z equal 4. Then you back substitute your z in here, and you will have a 2y equal -4 or y equal -2. Then you again back substitute z and y into the first equation, and that will give you the chance to find x. If you back substitute here, it will be 5. So if you have a system in this triangular shape or triangular form, back substitution, elementary step which gives you the solution straight away. So the Gaussian elimination method, it's the general algorithm which gives you 100% success converting any system of linear equations into the triangular form, which you then will be able to back substitute.